Howdy, we're the Experimental Electrochemical Cell team. Today we'll be presenting our virtual project showcase. We'll be presenting our Mechanical Engineering Capstone Senior Design Project. On the team we have Cameron Blackmon, Brandon Swearingen, Ashley Phillippi, and myself, Joelyn, Villame.
The problem was introduced to us by Dr. Matt Foy. He uses experimental electrochemical cells for thin film battery research. The current cell only has one window to view inside the cell through which the data is collected. He needs an improved cell to perform the same function in addition with a second window for visual observation in use. The importance of this cell is to allow Dr. Foy to study lithium batteries with the intention of improving their use and reliability of batteries in the future. Using this visual observation, he can study dendrite growth between the electrodes. The optical cell design requirements include viewing of electrodes and dendrites, allowing for two electrodes to fit in, as well as having a separation distance range. The cell needs to prevent lithium corrosion while being electrically isolated.
At the end of last semester, we created a 3D CAD model of our design that incorporated all design requirements. There were 3 prototypes created during this second semester: the aluminum prototype, the stainless steel prototype, and our final stainless steel prototype. During each iteration, we performed verification tests to ensure that all design requirements were fulfilled. During each new cell, we had a goal of optimizing all the features of the optical cell.
Some of the key features included in our final cell design include optical windows, electrode platforms and fixtures, a hermetically sealed cell, an electrically isolated cell, as well as cooling channels. The optical windows on the top and sides of the main body of the cell allow for MOS measurement and side viewing of dendrites for microscopic observation. The electrode fixtures, shown in the model on the right, clamp down the green-colored electrodes onto the platforms. Once the electrodes are fastened to the top and bottom sides of the cell must be hermetically sealed. This is to make sure that no oxygen can enter the cell and cause corrosion to appear on the electrodes. The next key feature for the performance of the electrochemical cell is the electrical isolation between the top and the bottom leads. If electrical current is able to pass through from the main body of the cell to the top red part of the cell, then there will be a short circuit between the anode and the cathode. The next aspect of our cell is the cooling channels. These cooling channels provide the ability to cool or heat up the reaction and cell to any desired temperature, making our cell more variable and able to perform different types of testing.
Throughout the project, the team wanted to minimize the cost for the project. The total cost spent on all materials and all prototypes was approximately $800, which was about $1,200 under our budget. The material cost for the final cell was approximately $130. Our final prototype is smaller, more ergonomic, adds cooling channels, and has successful validation testing. It also has the smallest electrolyte volume of all the prototypes, thus making the cost for each test much smaller. All of our design requirements are fully satisfied and fully operational with the MOS system. Thank you from the Electrochemical Cell team.